today we will discuss about the frame structure and then what is resource block and all. Okay. So before to discuss, okay, first of all in LT, we already have discussed, we have the scalable bandwidth, and that contains like the 5 bandwidths like 1.4, 3, 5, 10, 15 and 20. So when we schedule a data for any particular UV, okay, so overall resource block basically divides into the, so we have, for example, a 100 resource block, or you can say 20 megahertz. Let's not talk about the 100 resource block, it's 20 megahertz. So how we design our 20 megahertz, and then how design this whole 20 megahertz in the resources over the time domain and frequency domain, so that whenever MAC layer, especially I am telling you about the MAC layer, where scheduler is there, all the mind decision is taken over the scheduler. So whenever MAC layer schedules something to the UV, so it could decide how much resources. Currently I'm talking about how much resources, not talking about the resource block. How much resources can be assigned over the time and frequency domain. So this is what we will discuss. Then as far as the time domain is concerned, we have a frame structure, and that is 10 millisecond. Okay, and each frame has, okay, let me discuss from here. Okay, from here, so we have 10 millisecond of frame structure. Each frame has 1 millisecond. Okay, this is 1 millisecond, this is 1 millisecond, this is 1 millisecond, this is 1 millisecond, this is up to further in 1 millisecond we have 2 slot. Okay, something like that, 0.5 millisecond, 0.5 millisecond. Okay, and further in slot we have a symbol concept. Okay, so one slot has 7 OFDM symbol, OFDM symbol. We will discuss about the OFDM, but yes, as of now you just come to know we have some OFDM symbol. So frame, total frame, so this is complete frame of 10 millisecond. Then in 10 millisecond we have 10 subframe, and then in subframe we have further slot, like one subframe has one subframe has 2 slot. Okay, and each slot has 7 OFDM symbol, either 7 or 6. We will also discuss what is normal cyclic prefix and what is extended cyclic prefix and where we use this. Okay, but yes, as of now you come to know either 7 OFDM symbol or 6 OFDM symbol we accommodate. Okay, so this is basically the design. The difference for 4G and 5G is that still we have the same frame structure, only the scheduler granularity. Okay, so when we talk about the scheduling the data, so MAC layer always schedule minimum 1 millisecond. Okay, after minimum 1 millisecond, so that's why we call it TTI. TTI is 1 millisecond in TD in LTE. Okay, so what I'm trying to say is whenever we schedule the data in LT, so we'll have to schedule minimum in the time domain, minimum was one subframe. Okay, it means minimum 2 slot we need to assign. But while in NR, this scheduling is their granularity of this scheduling reduced up to the slot level. Okay, so in 5G we can schedule up to the slot level, but in LT we schedule up to the subframe level. Okay, so these are the one thing. So if we talk about like this, so we have 10 subframe in for the uplink and 10 subframe for the downlink. First of all, 10 subframe for uplink and 10 subframe for downlink. But in case of TDD, we do not have such leverage, we do not have such facility. So what we do, we have 10 subframe. In out of 10 subframe, we manage X subframe is for downlink, and 10 minus x is for uplink, because we have total 10. Okay, so for FDD we have separate like 10 for uplink and 10 for downlink, because we have a two duplex frequencies for uplink and downlink. Okay, and we call it type 1 frame. But in case of TDD, since we do not have that that facility, so obviously we need to manage our downlink and uplink in the same subframe. So since we have to manage downlink and uplink in the same subframe, so we have to make certain design. We have to create certain structure, so that in a subframe where uplink data is going, so we should not send the downlink data. Okay, so we basically structurized our whole 10 subframe into the downlink and uplink. So based on downlink and uplink, we have a different structures. We have seven structure. We will discuss about that as well. Okay, so this is basically the layer structure, or you can say the frame structure of FDD. You can see the TDD as well here. Okay, we will discuss about that. Okay, so when I was talking about the symbol, that is a 7, or this is slot and this is slot and this is the symbol. Okay, so let's discuss about symbol. How much? So this is basically our one millisecond, that is one subframe. Okay, under 1 millisecond we have 0.5 millisecond and then 0.5 millisecond, and this we call slot. Okay, this is one slot and this is one slot. Okay, then there is a definition of resource block RB. So definition of resource block is, okay, this was for the time domain. Okay, this was for the time. Let's discuss about the frequency domain. Let's discuss about the frequency domain. So I'm taking the example of 20 megahertz. Okay, let's suppose government has given us the 20 megahertz of 1.8 gigahertz of band. Okay, 1800 megahertz frequency, and then we want to deploy the LT over the 20 megahertz. So we have 20 megahertz. So generally what happened, we actually, as an operator, we really not able to use whole 20 megahertz, because it is 20 megahertz, and then there is another operator comes after this. Okay, so there we need to leave some guard band, so that the next operator, or you can say adjacent carrier interference, could be avoided, because here we have some interference. So that's why we do not use certain band. How much certain band? That varies technology to technology. Okay, so we do not use certain band. Okay, so that the interference could be avoided. So effective bandwidth is not 20 megahertz, that is less, that is 10% less. Okay, so 10% of 20 megahertz is 20 minus 10% of 20 is equal to 20 minus 2, that is 18 megahertz. Okay, so a rule, you can say, you just avoid 10% of the band from both. So 2 megahertz we have, so 1 megahertz from here and 1 megahertz from here, 5% from here, 5% from here, something like that. Okay, but in the same way, if we have an R, so rather than 10%, we use just 1%. Okay, 1%. So that is one of the achievement, kind of, it is more efficient. The reason behind, in OFD, in the LT we use OFDM, and in NR we use filtered OFDM. We will discuss about that. Okay, what is the, it's advanced version of the OFDM. Okay, we call it filtered OFDM, FOFDM. Okay, so it's kind of like your efficiency get increased, and you will have more resources for scheduling. So as of now, let's consider 20 megahertz is there, but effective bandwidth will be 18 megahertz, because 2 megahertz as a guard band we are not using. So 18 megahertz. Okay, so 18 megahertz. As also we know about, yesterday we will discuss about the subcarrier spacing. So we divide overall band into the 15 kilohertz of single subcarrier, 15 kilohertz of subcarrier spacing. Okay, SCS. Okay, so we want to calculate in LTE how many subcarrier spacing, so if we calculate like 18 megahertz is total band divided by 15 kilohertz, because every subcarrier spacing has 15 kilohertz. So total number of subcarrier spacing is 1200 subcarrier. Okay, so if you divide 18 divided by 15 is 1200. Similarly, you can calculate for 10 megahertz, you can calculate for 5 megahertz. So in case of 10 it will be 600, in case of 5 it will be 300. Okay, in case of 3 it will be something like 150, or maybe it is a little bit less, we can calculate on that part. Okay, so 600, 300. So depending on bandwidth you have some subcarrier spacing. Okay, now let's discuss about the resource block. Okay, so the definition of resource block is in the frequency domain 12 subcarrier, 12 subcarrier in the frequency domain, and 2 slot in the time domain. Sorry, 1 slot. So sorry, 1 slot in the time domain. So this we call it resource block. Actually, we call it PRB, physical resource block. So okay, so there is a very slight difference between the PRB and RB. Most of the people in industry use the same way like PRB and RB, though they are correct. Though they are correct, their intention is correct. But as a definition, if somebody say PRB is the unit of, it's bounded unit of frequency and time. So whenever we say this PRB, it means we are talking about the bounded structure of frequency and time. It means a 1 slot in the time domain and 12 subcarrier in the frequency domain is called one resource block, one PRB. But if somebody says RB is not bounded to the time domain. It's like how many subcarrier in the frequency domain, simple like this. These are the RBs. Okay, these are the RB. But yes, I mean the sense are same, so that's why the people use both in the same. I mean there is no just a matter of definition. Okay, so let's talk about as of now you consider PRB and RB as a calling is same. So the definition of one PRB, physical resource block, okay, is the 1 slot in time domain and 12 subcarrier in the frequency domain, and we call it one PRB. And this is the same in the NR as well. Okay, so if we further, so this is the smallest unit, you can say this is the smallest unit. But whenever we you can say schedule, we do not schedule 1 slot, minimum 2 slot we schedule. So minimum this particular block we schedule to any particular UV, a minimum to minimum this. It may be higher, mostly it is higher, like 2 RB, 3 RB, 4 RB, depending on how much data is required and what is the UV's RF condition. There are so many things actually. What is the buffer status report? What is the power headroom? What is their RF condition? How much how much UV is demanding? Okay, so there are so many factors actually. Based on that, scheduler decides how many PRB can be scheduled to this UV. Okay, first of all. Secondary, this particular RB, so if you talk about the structure wise, it's not like that. So this is this is one PRB, then similarly like second, like third, like fourth, something like that, up to this. How many PRB? Okay, so we have 1200 subcarrier, 1200 subcarrier. Okay, in 20 megahertz we have 1200 subcarrier. Okay, something like that. So one PRB has how many subcarrier? 12, 12 subcarrier. Okay, so 12 subcarrier. So how many PRB? It will be 100 PRB. Okay, so similarly like 100, 1, 2, 3, 4, like something like, I mean up to 100. This box will go like that. Okay, and in the time domain it will go up to the 10 millisecond. Okay, so somebody will be assigned like this. Okay, something like that. So currently this structure is only for this. Okay, this we are talking only about this. Okay, this is one thing. Further to that, when we talk about the symbol, okay, we will discuss how the symbol is generated, how the fast Fourier transform introduced in the picture, and then how the things are generated. Okay, we will discuss about that. But before to that, okay, so before to that, so if we talk about the 7 OFDM symbol, so how many total symbol will be there? That is 12 into 7. That is 84 OFDM symbol will be in one PRB. So 84 OFDM symbol. So this is one symbol, you can say. Okay, this is one symbol. This is one symbol. Oh, sorry. I'm so sorry. I just got confused. So this is one symbol. Okay, this is one symbol. Okay, this is one symbol. So we already discussed. We have 7 OFDM symbol. So total, how many small slot you will have? This how many this small unit you have? This we call the resource element. Resource element. So how many resource element? That will be 12 into 7. 84 in case of normal cyclic prefix. Okay, and in case of extended, 12 into 6, 72 resource element. Okay, in case of extended cyclic prefix. Okay, one thing. Further to that, the smallest unit is not resource element. The smallest unit is further in resource element. How many numbers? See, bit is the smallest. Okay, so bit is the smallest. So to calculate the bit under the resource element 6, I mean under the one resource element. So one resource element can carry either 6 bit or 8 bit or 4 bit or 2 bit or 1 bit. In which condition 8, 6, 4, 2? If we are using the modulation scheme 256 QAM. Okay, if we are using 64 QAM, we will discuss that as well. Okay, if we discuss 16 QAM, QPSK, and then BPSK. Okay, so depending upon what modulation scheme scheduler is assigning or UV is using, based on that, one resource element can have a different number of bits. Okay, so if we talk about the bits, so bits to resource element to symbol, okay, to, you can say PRB, something like that you can say. Okay, bit is the smallest unit, resource element, and then symbol, then PRB. But see, they are the units, they are the smallest, or you can say the different granularity of the unit. But whenever the assignment of the resource is concerned, we never assign bits, we never assign resource element, we never assign symbol, we always assign in terms of the PRB. Okay, so if we try to calculate how many bits in 1 millisecond, that is also you can calculate as in terms of the throughput. Sometimes the people say, I mean, what is the throughput? Okay, so we can calculate the throughput here. Give me just a second. Let me open that for you. So okay, so let's calculate a throughput kind of. See, we know that the MAC layer assigned per TTI, 1 TTI, 1 TTI, okay, 1 TTI, that is 1 millisecond. So let's calculate how many bit is basically transmitted in 1 millisecond. Okay, so in 1 millisecond, it means we have 2 resource block, first of all. Okay, because we already know in 1 millisecond we have 2 slot. Okay, so we have 2 slot. Sorry, in 1 millisecond we have 2 slot. Okay, so in one slot we have how many? So 84 resource element. Okay, we will talking about this resource element. Okay, this one. So but 2 slot has 84 into 2 resource element. Okay, so it's like that. So total how many PRB? Okay, this is 84 into 2. So you can calculate like that. It's like 12 subcarrier, 12 subcarrier. Okay, okay. 12 subcarrier multiplied by 2 slot multiplied by 7 OFDM symbol, okay. And then in every OFDM symbol we have 6 bit. I'm trying to calculate the maximum number of bit, max number of bit, okay. 6 bit, okay. In case of 64 QM, actually 64 QM is most popular. Currently we have 256 QM, but I'm talking about the 6 bit, okay. And this is for 1 PRB. This is equal to 1 PRB. 1 PRB. Or you can say in the time domain for 12 subcarrier. So similarly, we have, this is for 1 PRB. Okay, 1 PRB. But, sorry, 2 PRB in 1 millisecond. In 1 millisecond, I'm talking about. Okay. But we have similarly how many PRB? 100 PRB. So we can multiply it by 100 also. So 100 into 12 subcarrier into 2 slot into 7 OFDM symbol into 6 bit. 6 bit. So how much it will calculate? It will be around 1800 bits. But this number of bits is transmitting in 1 millisecond. Okay, let me tell you. Anybody has any confusion up to here, please? Hello? Okay, let's proceed then. So we are saying in 1 millisecond, scheduler is transmitting 10080 bits. Okay, so if you calculate in the bit per second, okay, so 1800 bits divided by 1 millisecond, that will be around 100.8 mbps. So this is, you can say, your LTE throughput in case of 20 megahertz. But you have actually, so this is theoretical peak. I mean, you are not taking any signaling, you are not considering any channel coding or anything. So if we calculate, I mean, if we take the 25% signaling in this, so it will be around like, 75 mbps. Okay, you can say 75 mbps. But this is in case when there is no MIMO. Okay, and one single user is there. And if we in case of 4 MIMO, so we can multiply it 75 into 4. Okay, that will be around 300. 300 mbps, around 300 mbps. Okay, so this is like theoretical, or you can say almost practical peak throughput that we achieve in case of 4x4 MIMO. Okay, so this is how, I mean, overall I'm trying to say this is how we calculate the throughput, okay, in 1 millisecond. Similarly, you can calculate in NR as well, depending on what subframe and what structures that you are using. Okay, say here, see number of resource block. Okay, so if you see here, you have 20 megahertz. Okay, you have 100 PRB. Okay, then 75 PRB for 15, 50 for 10. Okay, so similarly, like you have the number of resource block. If we talk about the subcarrier, okay, this one, you have 1200 subcarrier, then 900 subcarrier, then 600. How we calculate it? The 10%, we subtracted the 10% from there, and then we divided by 180. Okay, because 180, why? Because 12 subcarrier, 12 into 15. Okay, so this you can we will also come on this part as well. I mean, how we calculate the sampling. We will discuss about that. So as of now, I'm trying to say you. We will also discuss how this value come IFFT and all. We will also discuss about that. But as of now, you just know how many subcarrier and how the number of resource block you are calculating. Okay, let's calculate in TDD and not calculate. I mean, let's understand what is the structure of TDD. Okay, so in FDD it is very straightforward. Okay, we know this is uplink and this is downlink. So in FDD we very well know this is for, let's suppose, downlink and this is for uplink. Okay, we know. But in TDD we have downlink and uplink, we have to manage in between. Okay, so some part of the slot or some slot will be for downlink, or some subframe, sorry, not slot, some subframe will be for downlink, some subframe will be for uplink. So what are the possible structures for downlink and uplink? So these are the fixed, again I'm saying you, these are the fixed number of structures where TDD is deployed. Okay, so either, so how many subframe we have? 1 2 3 4 5 6 7 8 9 10 subframe. Okay, so they all are set seven I mean 10 subframe, but these are the different structure. So they are the fixed. So few things is noticeable that we will discuss here. I mean, how we can, how we can see. First of all, the first subframe will always be downlink. Okay, the first subframe will always be downlink. The reason behind it is, without without receiving anything for the assignment, or you can say the resource acknowledgement. Okay, we see UV will not transmit anything without having any grant. Okay, for example, UV want to upload something, but inodb will tell, okay, I am giving you the grant to upload because I have some resources you can do. So anyway, UV has to receive something in the downlink first. Okay, then it will transmit something to the uplink. Even if he want to do some upload, he needs something in the downlink. Okay, so first subframe will always be downlink. Okay, then from downlink to uplink, whenever there is a switching from downlink to uplink, there must be one SS, that is a special switching subframe. We will discuss why we need SS. Okay, but yes, as a thumb rule, you need to know from DL to UL. Every time if you want to do from DL to UL, you need a special switching subframe. Okay, a special switching subframe. But from UL to DL, from UL to DL, no need, no need. Okay, no need, no need for any special switching subframe. This is applicable for downlink to uplink. So it means, and second subframe will be SS. So of course, if this is SS, then it will be uplink. So this one is fixed. So these three structure is fixed. So downlink, SS, and uplink. Now you have only 1 2 3 4 5 6 7 options. Okay, these are just 7 options. Okay, so you can make kind of a permutation and combination, and you can make it like 7 structures. Okay, sorry. Okay, so these are the 7 structures. So downlink, SS, uplink, and from uplink to downlink, no need. Now the question is, if somebody is designing their network, okay, so it depends on the operator's purpose. Somebody say, okay, I have somewhere a requirement where the user's behavior or not download or something, they just want to upload. So if they want to make their network design for uploadable based, okay, not much downloadable, so what structure they will choose? They will choose this structure, okay, where we have more number of uplink, 1 2 3 4 5 6. Okay, here we have 6:2. Okay, or 6 is to, okay, 1 2 6:4 kind of. Okay, here we have 5:5:5. Okay, so this structure he will choose. SS, sorry, you can see the SS frame structure, subframe structure 0. Okay, But if somebody want to make their network or their particular cell more downloadable, so of course he will choose like this one, like this one. 1, 2, 3, 4, 5, 6, 7. Okay, so it's like the 8:2. Why I'm talking SS is always considered as 8. This is also further subdivided. We will discuss about that separately. So it's like that. So, and these are configurable with respect to the parameter of different vendors. You can configure based on your requirement. If you want to increase your throughput or something, and use, you feel like, okay, there is no upload, there is not much upload in my network, okay, then you can switch from some subframe to some another structures, okay. So all these frame configurations you can choose accordingly to your demand of your data, okay. Now let's discuss what is this SS subframe. That is, we call it special switching subframe. Okay. So the design of special switching subframe, first of all. Okay, first of all, let's discuss why we need from downlink to uplink, not from uplink to downlink. Okay, that we need to discuss here. Okay. So I am trying to discuss, we need a special switching subframe from D to U, but from U to D, no need. Okay. So there is a reason behind that. First of all, E node B is stationary and UV is moving. Okay, UV is moving, first of all. So I'm taking example DL. I'm taking this example. Let us suppose we have subframe, because see, both the subframe works on the E node B side. This is E node B, and this is you can consider the UV. Okay. So UV also has their own subframe. I mean, it runs, the clock runs both the way. DL, DL, then DL, then DL. Now, inode B sends some data. Inode B sends some data to UV. Okay, this UV. So the moment it will send this data to the UV, okay, it will not reach at this time, because there are two things. UV is moving, okay, or if it is not moving, then also there will be some delayed version. Okay, there will be some delay because of the profile of your, I mean, profile of your path. So you can say that because of the path distance. Let's suppose you have 2 kilometers or something. Okay, so you will have some path difference. They send here, but this data will have some delay version. Okay, so it will be delayed, and it is, let's suppose it is reaching like here. Okay, data is reaching here, then UV will also send. Okay, UV manipulate something and then it will also send. So it will not reach here, it will reach somewhere here. Okay, it is reaching here. But if we have uplink or downlink at this moment here, so this particular area will be interfered. So what we do, we create a guard period. We will have the guard period, GAURD, guard period, so that this area should not be collide or not be interference. Then we start as a uplink. Okay, then we start as a uplink. So that's why we put one special subframe, special switching subframe, because UV is moving. Then also we have, due to the path distance, the path delay is created, and delay causes the collision between uplink and downlink signal. Okay, that's why the guard period provides the enough time for, you can say, the downlink delayed signal to arrive due to the path distance, so that it will arrive at least the point where it should not collide. Okay, and also you can say it gives the sufficient opportunity for user, or you can say UV, okay, to receive the timing advance command, or you can say whatever signal is coming, because you know we sent the timing advance command. Okay, so that's why we do this guard period. But guard period distance is not that much. See, one slot has 0.5 millisecond, but guard period is not up to 0.5 millisecond. Guard period is very less. Okay, this is 0.5 millisecond, this is one slot, but guard period may be very small. But yes, guard period is required, and we know it is very important. But our constraint is we have a slot, we have to put the guard period, but unfortunately we do not require 0.5 millisecond for the guard period. So what we do, we put the guard period for some space, whatever is required. Then remaining spaces we utilize for downlink and uplink. Okay. So this is for downlink and this is for uplink. So that is why we call DWPTS, and this is UWPTS. Okay. Let me come here. Something like that. Okay. Discuss that. Where is that? Okay. Something like that. Okay. So we have a guard period. We required a guard period first of all, but guard period's length is not 0.5 millisecond. It is very less. Okay. So what we do, if we are not sending or receiving anything in this period, it will be unused. So what we have done, I mean, what the scheduler has done, it utilizes this area as well for data downlink. Okay. So that's why this whole special subframe has also different structure. This is also has different structure based on how much data you are sending for downlink and how much data you are sending for uplink, and then for the guard period. GP also has a different length, probably in some case where the UV is very high distance, 14 kilometer. So maybe GP is required very high because the signal which is coming, the very delayed version of signal is coming. Maybe UV is very near. Maybe the guard period length should be very less. So depending on the guard period length, okay, this special switching subframe has also different version. Okay, how many? We have 9 special switching subframe structures. Okay, where we have a different DWPTS and different UPPTS. Okay, so based on UV's position, UV's distance, we have a different guard period symbol. Okay, now in 0.5 millisecond, since we are designing 0.5 millisecond, so in 0.5 millisecond we have 14 OFDM symbol, sorry, 14 OFDM symbol. Okay, sorry, see, 1 millisecond, I'm so sorry. We have one complete subframe. Okay, this is our special switching subframe. So it has 2 slot. Okay, 2 slot. So it has 14 OFDM symbol because 7 plus 7 is 14 OFDM symbol. Now in 14 OFDM symbol, 14 OFDM symbol, okay, we have to design guard period as well, and then some symbol will be for uplink and some symbol will be for downlink. So if you sum this 3 plus 10 plus 1, 9 plus 4 plus 1, everything will be 14. Okay, so it will comes as a 14. But depending on situation of the UV is either near or far. These structures we decide where we want to give the less guard period, where we want to give the high guard period, where we want to go. So how it is designing, this is also have some calculation. I am taking the example of I'm taking the example of first, let's suppose TDD subframe 0. Okay, subframe, this is subframe. Again, I'm talking about the subframe structure. Okay, 0. So they are saying they have 3 downlink, 10 guard period, and 1 guard period. So we can calculate how much time we are taking for guard period. What is the duration? So these are the symbol, but we can calculate in terms of the duration. So total subframe 14 OFDM symbol is taking 0.5 millisecond. Okay. So one OFDM symbol will be 0.5 by 14. Then 10 OFDM symbol will be 0.5 by 4 into 10. Okay. So it's like that. So it will be 5 by 4. Okay. So something like that you can calculate. Okay. Okay. So sorry, 14. It will be 14 because this is 14. Okay. So 5 by 14 will be like something like, I mean, you can calculate like this much duration. Okay. This is the time. This is the time. That's why guard period symbol divide by total symbol. So guard period symbol is 10. Okay. Let me calculate again. That will be much easy. So guard period symbol is 10 divided by total symbol 14. Okay. So it will be like something like 0.00007. Okay. This is the time. This much time this guard period is taking. If this much time, we can calculate from how much distance the signal is coming to accommodate this. So we know the distance is equal to velocity into time. Okay. So time we already have time. Just give me 1 second. Okay. Total time, total distance, if we convert this time, see what we have done. We have a symbol, then from symbol we calculated the time, how much time this guard period is taking. Then from this time we are calculating the distance. Okay, so velocity is 3 into 10 to the power 8. Okay, I'm taking the velocity of electromagnetic signal. Okay, 10 to the power 8, but this is in vacuum. Of course we are having some medium, that is air interface. So we'll have some permittivity of the free space and sensitivity of the free space. Those constant we can add, but yes, as a concept, 3 into 10 to the power 8 multiplied by like this time 0.007, 0.0007. So it is coming around 214 kilometer. 214 kilometer. But this is round trip because some signal is going, reflecting, and UV is coming. So this distance is for round trip. So for one way it will be like 107 kilometer. Now let's build the concept from this calculation. It means if the UV is up to 103 kilometer, let's thinking reverse way. If UV is at 107 kilometer or 100 kilometer, then it will be required 10 OFDM symbol to accommodate, to avoid the interference. If some user is at 10 kilometer, it will require like only one OFDM symbol. So depending on your cell profile, okay, depending on your cell profile, if you are in the dense urban, rural, or you are designing somewhere in the hilly terrain, so based on that, you know what is your profiling, what is your cell radius. Okay, so based on your cell radius, you calculate the distance, and then based on that you calculate the symbol. Okay, so based on this symbol you then design your downlink and uplink. Okay, so for example, generally SS7 is the most used case, like SS7, this is we call SS7. Okay, generally we design for 14 kilometer. Okay, 14 kilometer cell radius. So 14 will be like either this one, because 11 will not accommodate, either this accommodate or this accommodate. Okay, so we can take either this or this. Okay, so sorry, we can take either this or this. So if we take this, then it will be 11. It will be 11 downlink and one uplink. And if we take this one, then we have 10 downlink and 2 uplink. So it depends, either you can take this or you can take this. Okay, the benefit of taking this is we have downlink and uplink both. At least we are accommodating at one more symbol for uplink. But here we are more downloadable, less uploadable in case of switching subframe. And this is structure is only for switching subframe. So there are 3-4 things we have discussed. One is total frame, then we have subframe. How many structures we have? This is the 7 structure. Further is this is switching subframe. We have different structures, like 9 structures of switching subframe. In the 9 structure of switching subframe is decided based on how much guard period, or this guard period is decided based on how much cell radius is there of the UV. Okay, so these are the designing that you do, and then you actually tune your parameter. Okay, but yes, as a concept, you guys must know what is DWPTS, what is UBPTS, what is this guard period, and how we decide in which conditions we need less guard period, in which condition we need more guard period. Okay, what are the TDD subframe configurations, all these things you must know. Okay,